So we've begun to see that equilibrium problems get a little bit more complicated when the number of moles of reactants on the left side of the reaction are different than the number of moles of products on the right side of the reaction. So for example, we've considered the two cases H2 and Br2 form two HBRs. So in this case, the sum of all the stoichiometric coefficients is 0, because if I consume 1 mole of H2 and 1 mole of Br2, I produce 2 moles of HBr. The stoichiometric coefficients, -1 and -1 for the reactants, and +2 for the products, those sum to 0. In that case, everything was relatively simple. My equilibrium constant, which is number of product molecules divided by number of reactant molecules, raised to their stoichiometric coefficients. It doesn't matter whether I work that problem in terms of number of molecules, as I've written here with capital N, or number of moles, as I've written with a lowercase n. Because since I have moles squared in the numerator, moles squared in the denominator, the units of moles cancel and everything is fine. Doesn't matter whether we work in moles or in molecules. On the other hand, when the sum of the stoichiometric coefficients is not 0, like in our bromine formation reaction, 2 bromine atoms form 1 bromine molecule, I've gone from 2 molecules of reactants to 1 molecule of product. So the sum of the stoichiometric coefficients in this case is not 0, then it does matter if I work in moles or not. The correct thing to do is to think of the equilibrium constant as molecules of bromine divided by molecules of atomic bromine squared. That will not be the same number as moles of bromine gas divided by moles of atomic bromine squared. So this is not the right way to think about the equilibrium problem. Just to make sure that point is clear with an example, because it might seem very counterintuitive. Let's do an example with some numbers. So let's say we're thinking about this 2Br forms Br2 reaction. We've seen that the equilibrium constant for that reaction is 1.6 times 10 to the 7th when we're at a temperature of 298 Kelvin and a volume of 1 liter. Let's suppose we start with the initial conditions of 1 mole of Br2. So I've got a mole of bromine gas, Br2, which I can express either in terms of moles or I can express as capital N is 6 times 10 to the 23rd molecules of Br2. And I have no bromine atoms, none of the reactant present. And the question is going to be, once this reaction reaches equilibrium, how many of those Br2 molecules would dissociate and how many Br atoms will they have formed, or if we prefer, how many moles of bromine atoms have they produced. So notice, first of all, since I've given initial conditions that have exclusively 100% product and no reactant, we know for sure this reaction is going to go in the negative direction. It's going to proceed backwards, so we should expect to find, that's supposed to be a C, a squiggle. Our extent of reaction should be less than 0. We're going to get a negative extent of reaction for this case. When we begin working the problem, we start like we usually do by saying the equilibrium constant, which is some number that we know, is equal to products divided by reactants, moles of bromine 2 divided by moles of bromine atoms squared. We know that if the reaction proceeds to some extent squiggle, the number of Br2 atoms, remember hypothetically if the reaction is proceeding forwards, every time the reaction goes forward 1 time, I gain 1 Br2 molecule. So I've got some initial number of Br2 molecules plus squiggle. Every time the reaction proceeds, once I lose 2 bromine atoms, so I've got -2 squiggle bromine atoms, the 0 that I started with minus 2 squiggle, and that's squared in the denominator. So expand that square. Then I've got this expression. If I rearrange these two pieces, K is equal to N naught plus squiggle divided by 4 squiggle squared, multiply through by 4 squiggle, and collect all the terms on one side. I see 4 times K times squiggle squared minus this squiggle minus N naught gives me 0. So I've rearranged it now in this form. It looks like a quadratic equation. I want to solve for the value of squiggle. So working that through in detail the first time, squiggle is going to be equal to what the quadratic equation says it should be, negative b plus or minus the square root of b squared minus 4ac over 2a. So if I plug in 4k for a, -1 for b, negative n naught for c, into the quadratic equation, I get this, and then if I plug in actual numbers, K, remember, was 1.6 times 10 to the 7th. My initial number of molecules was 6 times 10 to the 23rd. If I plug those numbers in, quadratic equation has two solutions. We find either that the extent of reaction is 9.7 times 10 to the 7th or negative 9.7 times 10 to the 7th from this plus or minus term. Remember, we expect that the reaction should go backwards. I don't have any reactants, so it's not possible for the reaction to go forwards. There's no reactants to consume, so the positive squiggle is physically impossible. The negative result is the one that's physically meaningful. So my solution is the extent of reaction is this number, minus 9.7 times 10 to the 7th. That means the number of each species that I have at equilibrium. Number of bromine is initial amount plus squiggle. So 1 mole minus 9.7 times 10 to the 7th molecules. 10 to the 7th is insignificant compared to the 10 to the 23rd, so that just works out to pretty much the same 1 mole I started with, only a negligible fraction of the Br2 has dissociated. For bromine atoms, the amount of bromine atoms I have is negative 2 squiggle. If I multiply negative 2 by my solution for squiggle, then I find that I've got 1.9 times 10 to the 8th bromine atoms. If I do convert that to moles, I find that that's this fairly insignificant number of moles. I've got 3.2 times 10 to the minus 16th moles of Br atoms. So that's the answer to the question I posed. Let's remember this number to compare it to what we get in just a second if I mistakenly attempt to solve this problem using moles instead of molecules. So if I were to say equilibrium constant is products divided by reactants, but if I write that as moles of Br2 over moles of Br squared, immediately I know that this is not the right thing to do because the value of K that I've been given, remember, K is 1.6 times 10 to the 7th with no units. That's a unitless quantity. So I've got a unitless quantity for K. Moles divided by moles squared, that should come out with units of 1 over moles. So already I'm in unit trouble if I even write down this equation. The quantity on the left is unitless. The quantity on the right has units of 1 over moles. So I know this is not the right thing to be doing. But if I were to not notice that and proceed, algebraically the solution works just like it did in the previous example, except now I'm using lowercase n for moles instead of capital N for molecules. Quadratic equation works the same way. Equilibrium constant's the same number, but if I plug in 1 for the initial amount of moles instead of 6 times 10 to the 23rd, I find that the physically relevant solution is negative 0.0001 moles. So this result is different than the answer I got when I used molecules, and this is the wrong answer, again, because it's not correct to be using moles in this expression. So this whole approach is invalid. We shouldn't have done that in the first place. I'm just illustrating it to show you that you will get a different answer and the wrong answer if you use moles instead of molecules in a problem like this one where the units of moles don't happen to cancel. To find out what we should have done instead, if we insisted on working the problem in moles, which is usually more convenient, what we know is true is that the equilibrium constant is molecules of Br2 over molecules of Br squared. I can label that equilibrium constant K sub capital N to emphasize the fact that that's an equilibrium constant expressed in terms of molecules. If I did want to find out what the equilibrium constant would be expressed in terms of moles, K sub little n, then what I want to find out is what is equal to moles of Br2 divided by moles of Br squared. The moles of any quantity is just the number of molecules divided by the Avogadro's number. So moles of Br2 is molecules of Br2 divided by Avogadro's number. Moles of Br is molecules of Br divided by Avogadro's number. I can simplify that expression. I've got an NBr2, capital NBr2 in the numerator, capital NBr squared in the denominator. Sum of the Avogadro's numbers cancel, and I end up with 1 Avogadro's number to the plus 1 power. So what we found is that in this case, equilibrium constant written in terms of moles is equal to the equilibrium constant that we already know that's written in terms of molecules. Br2 over Br squared multiplied by Avogadro's number. So that's the unit difference between an equilibrium constant expressed in terms of moles and molecules. In this case, our equilibrium constant expressed in terms of molecules, if I multiply that by Avogadro's number, I find what the value should have been if I wanted to work the problem in terms of moles. So we won't do it, but if you go back and work the problem using moles, if we use the correct value of Avogadro's, of the equilibrium constant expressed in terms of moles, we would get the right answer in this case. More generally, in a case that's not just the Br2 formation reaction, it's always true that the equilibrium constant expressed in terms of molecules is molecules of product divided by molecules of reactants raised to their stoichiometric coefficients. So the product of these n's raised to their stoichiometric coefficients. If I want to write it in terms of moles, that's the product of moles raised to their stoichiometric coefficients. Again, if I convert moles, if I express the number of moles as molecules, capital N divided by Avogadro's number, then I have this expression. The moles of each species need to remain inside this product notation, but Avogadro's number is the same number for every species. So I can pull the Avogadro's number out of the product. So I've got 1 over Avogadro's number raised to each of these stoichiometric coefficients. So after I've pulled it out, I've got 1 over Avogadro's number raised to the power, the sum of all the stoichiometric coefficients, all still multiplied by the product of the molecules raised to their stoichiometric coefficients. The sum of the stoichiometric coefficients, this quantity right here, we're going to write that as delta nu, the net change in the stoichiometric coefficients. So if I have a reaction like H2 and Br2 form 2 HBRs, if I destroy 2 molecules to create 2 molecules, and then the sum of the change in the number of moles is 0. But for a reaction like the Br forming Br2 reaction, if I destroy 2 molecules to make only 1 molecule of Br2, then I've lost 1 molecule of gas every time I do the reaction. So that would have a change in moles of delta nu equals -1. So going back to this result, my equilibrium constant written in terms of moles is equal to 1 over Avogadro's number raised to the change in number of moles times the equilibrium constant written in terms of molecules. So that's a result that's worth remembering if you want to convert back and forth. If you know the equilibrium constant, perhaps you've gotten it from partition functions, the equilibrium constant written in terms of molecules, but it's more convenient to solve the problem in terms of moles, then this is how you convert from one to the other. And as a last comment, notice that the very first statement we made in this lecture, which was that for a molecule which doesn't change the number of moles from reactants to products, if it has the same number of molecules on the reactant side as it does on the product side, in that case, the change in number of moles will be 0, and I don't need to include any factors of Avogadro's number when converting from moles to molecules. So that's why for the initial H2 plus Br2 reaction that we've considered, we didn't have to think about this because the change in number of molecules was 0 and this conversion factor dropped out.